Welcome everyone. In this video we will see how we can express velocity in polar coordinates. So let me first draw a Cartesian plane and then we will also have the polar coordinates. So this is the classic Cartesian plane. We have the x-axis and the y-axis. And let's say that we are interested in this point. The particle, the object, the mass, whatever we're dealing with is at that point. We could express its position in terms of x and y, as we are very familiar with this. And we can also express it in terms of polar coordinates. For that, we draw from the origin, we draw a radius, r, and this is a vector. And then there will be an angle of theta. Okay? And it is, as you can see, measured from the positive x-axis. I'm talking about the angle theta. Now, if we want to, so now this is r, this is the position of the object. And if we want to express this in terms of Cartesian coordinates, we can simply do this. R is going to be, it is going to have an x component, and the x component is simply, well, it's x, and it is in the x hat direction, then plus y, and now y hat direction. The velocity is the derivative of this with respect to time, the derivative of the position, dr by dt. And so how do we take this derivative? We simply do dx by dt x hat plus dy by dt y hat. This is fairly simple, right? And in fact, when I wrote this, at this step, there is something happening behind the closed doors. I am saying it in a poetic way to give it more emphasis. When I wrote this, in fact, there is something going on. And you might be wondering, like, what is going on? Is this wrong? This is not wrong. But most of the time, and especially if we haven't dealt with polar coordinates much, most of the time, we just write this with making an assumption that is correct, but we don't pay attention to what we're doing. And it will be quite important that we pay attention to what we're doing in polar coordinates, because some assumption that we might be tempted to make won't be true, in fact, for the polar coordinates. And I know what I just said may sound very complicated. I did that on purpose because I think that complication also, creates a sense of mystery. And I want you to watch this video with a sense of mystery so that you're more engaged with it. And that sense of mystery, well, it will be gone in like a couple of minutes, so don't worry. Okay, this is it. Now back to the physics. Now, alright. And also, these are the x and y coordinates, as I said, the axes, You can also think of them as if you want, maybe it is more helpful in this case, x hat and y hat directions. Now, for the polar coordinates, we get to define two other unit vectors. One of them is the r hat unit vector. It is like this. And the other is going to be the theta hat unit vector. What is special is that they are perpendicular to each other, just like x and y. So, and, well, let's keep the perpendicular sign. Okay. So the thing is, how do we express the position vector r in polar coordinates? It is going to be magnitude of the vector, which I will call r, and then r hat. It is so simple. Now comes the part. We will take the derivative to find the velocity. With respect to time, we take the derivative. This is the velocity and the derivative with respect to time. What is this? We know how it is done. Look at this example. It is going to be dr by dt r hat, right? And no, this is not correct. And this is the mystery that I was talking about. This is the point where we need to pay attention to what has been happening behind the closed doors. Here, for example here, when I took the derivative, what I did was, in fact, even if I did not do it on purpose, what is happening is we are taking the derivative of a product. We have x times x hat. So in fact, the derivative of x times x hat is dx by dt x hat plus dx hat by dt then x. However, since the Cartesian unit vectors x hat and y hat don't change, does not change, they are not changing with respect to time, this derivative is 0. So this simplifies and we are left with this. And similarly for the other term in the derivative as well. This is what was happening behind the closed doors. And as I said, you might have already been aware of this and you were keeping in mind that x hat was a constant. But in case you didn't realize that, it is important that we come to this realization because here r hat is not a constant. Why is it not a constant? Well, because let's say the particle moved here. Now the unit vector is like this. And the r hat is now like this. As you can see, it changed direction. So r hat is something that changes direction with respect to time. And let me erase all of these so we have more space to work with. So now the question is, how do we take this derivative then? And we will first of all use the product rule. So it's going to be dr by dt r hat plus dr hat by dt r. Right? And here, the thing that, you could stop here. This is perfectly fine. This is correct. But the answer that I want is in terms of theta hat and r hat. And of course, it can also depend on the magnitude of the position, but we will see it by the end of the video. So what I'm trying to say is, I don't want this. I want to get rid of this derivative. It is looking very complicated. Maybe I can simplify it. Maybe I can write something better for it. So how do we take the derivative of r hat with respect to time? Maybe the first thing that comes to mind is to express r hat in terms of the Cartesian coordinates. Because we are more familiar with the Cartesian unit vectors, why not express r hat in terms of them? So let's do that. If I were to draw a line like this, a dashed line, this is going to be theta. So let's change color. So r hat is going to be, and I am using the Cartesian coordinates now. It is going to be, well, it's going to have a cosine. So cosine of theta x hat plus sine of theta y hat. And the reason that we only have cosine and sine is because the magnitude of the unit vector is 1. So you can think of this as 1 times cosine and 1 times sine. And in fact, if we were to find the magnitude of r hat from this, you square each component and then you add the squares. So cosine squared plus sine squared, that is 1. So in fact, r hat is a unit vector. This is r hat. What about theta hat? Theta hat is going to be, well, let me do another dashed line. This is vertical. This part is 90 degrees minus theta. So this part is theta. Which means that, and look at this, it is in the negative x direction. So it's going to be negative sine of theta x hat plus cosine of theta y hat. Cool. So we can now take the derivative of r hat with respect to time. We are going to use this expression. dr hat by dt. It is going to be equal to. And notice that this part is easy to take. The derivative is easy to take for this because we are again dealing with x hat and y hat, which are constants. What is the derivative of cosine of theta? Well, it's going to be negative sine of theta only if we are taking the derivative with respect to theta. But we are taking it with respect to dt. Time. So we also need to multiply this by the derivative of theta with respect to time. We are using the chain rule here. We're going to have x hat plus derivative of sine of theta with respect to theta is cosine of theta. We also write the derivative of theta with respect to time and then y hat. So let's continue on the, well, okay, so this is going to be equal to further along. If we take the d theta by dt out, d theta by dt, it's going to be negative sine of theta x hat plus cosine of theta y hat. And this part, I hope, looks familiar to you. Look at here. Exactly. That is theta hat. We have d theta by dt and then theta hat. So now we can substitute for it. So we can substitute for this expression. Which means that v, the velocity in polar coordinates, is going to be dr by dt r hat plus d theta by dt r and then theta hat. And another, a more concise way of writing this is using Newton's notation for the derivatives, r dot r hat plus r theta dot theta hat. And this is it. This is how you express velocity in terms of polar coordinates. Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. And if you want to see further videos like this, please make sure to subscribe. I hope to see you in another video. Until then, take care.